I want to start this video with a question. Can you fill in the following square with the numbers 1 through 9 such that each row, column, and diagonal all sum to the same number? So you just take a 3 by 3 square and just fill in these numbers 1 through 9, and then you should get each row, each column, and then each diagonal all sum to the same thing. So take a minute, pause this video, and see if you could find one solution to this. One thing that will maybe help you out with this is that, well, the thing that they all have to add up to is fixed. So, for example, let me move this over here. So if you add up all of the numbers from 1 through 9, so here's like one really bad guess for this, because you know the first row of this is going to add to 6, and then the last row is going to add to 24. But if you were to add up all of the numbers from 1 through 9, and then divide by 3, what do you get? Well, you should get, I believe the answer is 15. Why am I dividing by 3? Well, these numbers have to go into the squares in some order, some permutation. And so each row should have 1/3 of the total sum. You could do this for like each column too. Doesn't really matter, but so anyway, try and figure this out. What should the entries be if each row and each column and each diagonal all have to add up to 15? So pause the video and give that a shot. Okay, I'm going to assume that you've had a chance to try this. Here is one solution. You start by putting 4, 5, 6 along the first diagonal, and then, well, maybe I'll tell you how you might find it if you knew that 4, 5, and 6 had to go along the diagonal to start. So you can't put a 1 right here or right here, because if you did, then this first column would have to add up to 15, and so this would have to be a 10 for that to happen, but the biggest number that we can pick is a 9. So the 1 can't go there. It has to, and it also can't go here for the same reason, or here. So it has to go either here or here, and it doesn't matter which one we pick, up to symmetry. So we'll pick here. All right, now the second column right here has entries 5 and 1. So this entry should be a 9, so that all adds up to 15. Similarly, this entry should be an 8, so that row adds to 15. Now the first column adds to 12 right now, so I'll put a 3 right there. The second row adds up to 8 right now, so I'll put a 7 right there. And then what's this last entry need to be? Well, the first row adds up to 13 so far, so that'll be a 2. And then we should check that this adds 15, and that's 2 plus 7 plus 6, that's 9 plus 6, yeah, that's 15. And then 8 plus 2 is plus 5, that's 15. So this works. Okay, so that's one solution. So definition: an n by n square, or matrix, filled with numbers such that each row, column, and diagonal all add up to the same thing, all have the same sum, is called a magic square. Sometimes we call the thing that they add up to the magic number for that square. So for example, this is a magic square with magic number 15. Okay. Note that this definition is allowing for more things than maybe you would originally think. So, as an example, if you're allowed to just make all of the entries the same exact thing, and then this definition would be satisfied. So if you make all of the entries 0, then each row adds up to 0, each column adds up to 0, and each diagonal adds up to 0. Same thing for a matrix of all 7s. Like each row would add up to 21, each column, and each diagonal adds up to 21. So these are like your really basic examples of what magic squares could look like. Yeah. So the thing that we were working with before is called a normal magic square. So a magic square is normal if it's filled with the numbers. So this is an n by n magic square. So this is right here is like a 3 by 3 magic square. 3 by 3, that would add up. That would be 9 total entries. I have 3 rows, 3 columns, so 3 squared total entries. And you see if you have an n by n square or matrix, then that would have n times n, which is n squared entries. So a magic square is normal if it's filled with the numbers 1 through n squared. Okay, so that's what we were looking at before. So counting the number of normal magic squares is very hard, and it's kind of an open problem right now, actually. I don't know what partial answers are out there for this as of this recording, but if you're interested, maybe go take a look. The book gives at least one reference that you could look at if you're interested in this problem. I think it's pretty interesting. But anyway, this is a hard open problem that not many people know a lot about. So what do you do when you have an open problem in math that you don't know how to deal with? Well, a lot of times you just simplify the problem and work on an easier problem so that maybe you can build up to the harder problem. So what we'll do is we will try and count the number of magic squares that are not necessarily normal. So just like any magic square that might just look like these or these, it doesn't matter. Just no limitations on the square being normal. Okay. Well, you might guess, you might immediately see that the number of magic squares, the number of 3 by 3 magic squares is infinite already, just because if you look at this example, you could have a magic square with all entries being 0, all entries being 1, all entries being 2, 3, 4. So already there are infinitely many that you can count right there. So what do we mean by counting them? Well, first, to say that, let me say this. So we can take the set of n by n magic squares and we can form a vector space out of them. And so the idea for counting the number of magic squares is we're going to calculate the dimension of these vector spaces. So the set of n by n magic squares forms a vector space, which we're going to be denoting by m sub n. So if a and b are magic squares and r is a real number, then a plus b is going to be a magic square, and r times a is going to be a magic square. Why are these things true? Well, so if a and b are magic squares, then that tells you that each row, each column, and each diagonal of a, and similarly for b, are going to add to the same magic number. So for a, maybe each row adds up to 17, and for b, each row adds up to 11, then the corresponding rows in a plus b are going to add up to 17 plus 11, which would be 28. So the magic number for a plus b would be just the magic number of a plus the magic number of b, which in this case is 28. And so yeah. And then the same thing holds for if you scale an entire magic square, scale an entire matrix. If each row adds up to 15 and you're multiplying that entire row by 2, then that row would add up to 30. And same for each column and same for each diagonal. So So the sum of two magic squares is going to be a magic square, and if you scale a magic square, that'll also be a magic square. In other words, we just did the subspace test for Mn as a subspace of the vector space of n by n matrices. So this is a vector subspace of the set of n by n matrices. Oh, also maybe note that we already know that this set is non-empty for any n because the magic square with all zeros is going to be in there. So this is a non-empty subspace of the set of n by n matrices, that vector space. Okay, cool. All right, going even further, the set of n by n magic squares with magic number 0 is also a subspace. So we're going to denote that by m sub n comma 0. So this is a subspace of m sub n. And why is that true? Well, same sort of reasoning. So we already know that if you add two magic squares together, you get a magic square. And if you scale a magic square, you get a magic square. What if the magic number of a and b were both equal to 0? Well, then a plus b, as I was saying before, the magic number of a plus b would be the magic number of a plus the magic number of b. And if both of those are 0, then the new magic number should also be 0. And then same for if you scale a matrix with magic number 0 by any constant r, your new magic number would be r times 0, which is still 0. So mn0 is also a subspace of m sub n. So, like I said, now that we know that these are vector spaces, we are going to compute the dimensions of these vector spaces